afternoon to our East Coast attendees and good morning to our West Coast attendees. My name is Hunter Wack, Business Development Manager here at Rayco Rents. Thank you all for taking time out of your busy schedules to join us for this webinar today. Our presenter today is Dusty Ott with SKC Inc. He is going to give us an in-depth look at how to sample using a SKC Parallel Particle Impactor for silica sampling to ensure that your silica monitoring projects go smoothly. Some topics they will cover today include understanding how size-selective samplers work and why they matter for silica sampling, learn what makes a SKC PPI unique and how it performs compared to traditional cyclones and cassettes, break down the true cost of sampling, including the risk of quote-unquote bad data, gain practical tips for successful field use and data interpretation. Dusty is a CIH with SKC that focuses on product technical knowledge, sampling procedures, and high-quality service. Dusty has been a great resource for Rayco Rents, providing technical insight to all SKC's products. Whether it was at a conference or an AIHA event, it's always nice to have a friendly, reliable face that understands the equipment, different sampling needs, and analytical procedures at a deep level such as Dusty. Since we have a large number of attendees, everyone will be muted. We do have a chat box that you can use to ask any questions or leave comments. We will try to answer all questions at the end of the presentation if we have enough time. About 1 or 2 hours after the webinar, you'll receive a certificate of attendance along with a recording of the webinar. If you don't receive this, feel free to send us an email and we'll send that over to you. The webinar will also be posted on our website for you to view at any time for free. I'm going to turn the mic over to Dusty and let him take the lead. Welcome, Dusty.
Thank you, Hunter. I appreciate that. And I just wanted to point out, like you told me earlier, that if we do run a little bit late, we'll be able to get to all the questions that we have this time. We don't have that hard cutoff like we did last time. So that's awesome. So thank you, everybody, for attending. Like Hunter said, we're going to be talking about the PPI. We're going to talk a little bit about cyclones as well and how they differ, where they're good, where they're not so good, what is going to be the best choice for you as you decide moving forward in your silica sampling. And so, kind of like the title says, understanding the dynamics of size-selective samplers. There's a lot of things that are very important for us to understand. So we're going to start at a fairly basic level and kind of ramp up from there. So if you've done silica sampling in the past, don't feel like that you already know all this stuff. You probably do. Just understand that we're going to ramp up to accommodate everybody on here, whether you're a seasoned pro or this might be your first introduction to some silica sampling. And so kind of like Hunter already talked about, these are our learning objectives today. So I'm not going to cover these again because he did a great job of doing that. But as far as the outline of how the flow is going to work today, we're going to talk about silica accuracy and why it matters. We're going to talk about size-selective sampling and how each one is a little bit different and how they collect those particles in a very unique way. Talk about the SKC PPI, how it's different, how it's similar, some do's and don'ts of silica sampling for both the PPI and a cyclone, and talk about some effects of using a wrong flow rate. If anyone's done any size-selective sampling in the past, there's a good chance that at least one time they've accidentally used the wrong flow rate. We'll talk about that a little bit, and then we're going to get into what sampling actually costs from an actual labor point of view, from an analytical point of view, from a bad data point of view. So to try to give you a really good idea of what the actual financial burden is on yourself or a company that goes into silica sampling. So with that said, we're going to talk about the invisible danger of silica and how it's something that you cannot see with the naked eye. And so as you zoom in and in and in, what looks like a little shiny, sharp arrowhead is actually a silica particle that has been magnified a ton. Now, as you look at this particle, you'll see that it's very jagged, it's very sharp, and you can imagine if this was life size, you definitely wouldn't want to handle that without gloves on, because there's a good chance it's going to cut your hands. Just like this on a microscopic level is going to go deep down inside of your lungs and cut up your alveoli. So it makes it harder for you to breathe over a long term. So this is something that none of us will be able to see with our naked eye, but if we could see it, I think you would treat it a whole lot differently than we do out in the field normally. So respirable silica, like I said, it's microscopic, it's very sharp, and it has a crystalline structure. Now, these small particles are able to travel deep down into your lungs and cause problems. What happens is, as these particles travel deep into your lungs, they embed in your alveoli. White blood cells come along and try to take care of them because they're a foreign body. Well, what happens with those white blood cells is, as they try to consume that small piece of silica, all those sharp edges that are cutting your lungs also cut open the white blood cells. As those white blood cells are sliced open, they release cytokines that go and tell other white blood cells, hey, I need help. So they come to that site and try to digest and eat that piece of silica, and more of them die. And over time, like it says on the bottom here, years or decades later, all those white blood cells that have died cause a scar tissue inside of your lungs that prevent you from using your lungs like you normally would. The lungs lose their elasticity, and you can no longer take in the big breaths that we normally can. And this is the whole point of what we're trying to avoid. We're trying to detect and figure out how much dust and silica is in the air, so we can implement proper controls to reduce the hazard to workers out in the field. So this is very important to consider. Is size-selective sampling, it's selectively capturing the particles based on the health effects that they are going to cause. And so if we were sampling for something that would have a health effect no matter where it was deposited in our body, whether in our nose, in our mouth, in our throat, we wouldn't necessarily need to use a size-selective sampler. But because we are trying to capture those very small particles that travel deep down inside of our lungs, we have to use a specific device to capture those smaller particles. And so the size of particles that we are talking about are in this range right here. They're from that 1 micron up to about 10 microns. Now, you'll notice that red blood cells are larger than some of these silica particles that travel deep into our lungs. And then on the same hand, there is some bacteria that are the same size as these very small silica particles that travel deep into our lungs. And so you also notice this line right here above the 10 micron line. This is where the ability for our eyes to see that in the air diminishes. We cannot see these size of particles in the air, but we know they're there. And these are the sizes of particles that we are specifically trying to capture on our filters, whether that's with a cyclone or with a PPI. That's what's being sent off to a lab to be analyzed. So again, we are talking about extremely small particles that we cannot see in the air that are doing damage deep down in our lungs that takes years or decades to manifest. So sometimes it's a very hard concept for workers and management to get their head around, because you can't see it, you can't smell it, you don't know what it's doing right now, it's not hurting you right now, but it just takes a long time to manifest in our bodies. And so let's talk briefly about collection efficiency and what that means. So if you look at this graph, the dotted line, this is the ISO 7708 1995 respirable curve. And you'll notice along the way that there are different efficiencies that these particles are being collected. We're going to start at 4 microns because this is what matters when it comes to what we're talking about. At 4 microns, our samplers, whether you're using a cyclone or whether you're using a PPI, it is collecting 50% of particles that are 4 microns. If we go up this graph, say to something that's along the line of 2 microns, we follow that line up the graph and we find that these samplers are collecting about 90% of particles that are 2 microns. You go even further up the ride, down to the half micron, 1 micron range, and these samplers are collecting almost 100% of those particles. That means that all of those particles that are the size of bacteria are being collected by this sampler and collected on that 37 millimeter filter that's either in your cassette for a cyclone or for your PPI. On the other hand, as you go down this line, if we're looking at something that's around the size of 6 microns, these samplers are only collecting about 15 to 20% of those particles. And as you work your way all the way out to 10 microns, these are collecting less than 1% of those particles. And where this matters is it mimics what our body is doing at the same token. If you've ever been in a very dusty environment, whether you're on a four-wheeler ride, out jeeping, just out in a dust storm, you get home and you blow your nose, you have a lot of dust that's in either your snot or your mucus, whatever it might be. And that is because these larger particles are being removed by our body through impaction. So I have written down on the bottom here that we are our own oiled impactor. That'll make a little more sense as we go along. But every time that air goes into our body, whether through our nose or through our mouth, it makes a lot of very tight turns as it travels down deep into our lungs. And as we travel deep into our lungs, there's a lot of spots for those larger particles to impact out and to be removed by our body. Our body is really, really good at getting rid of the larger particles that aren't going to hurt us. It's not so good at removing the very, very small particles because they remain suspended in the airstream all the way down deep into your lungs. So the two size-selective samplers that we are going to talk about today, like I mentioned earlier, on the left, you'll see cyclones, and on the right, you see impactors. They are both effective at removing the larger particles. There's pros and cons of each, and we're going to get into a little bit of those as well. There are numerous other types of size-selective samplers, but these are the two that we are going to primarily focus on today. So the basic operation of a cyclone, if you've never seen inside one, it's kind of fun and interesting. You have an inlet. This is where, if you look at the cyclones that you've used, there might be 1 or 3 different openings that air and dust travel into the cyclone. As soon as the airstream travels into the inlets, it is spun into a vortex. Now, from that point, the larger particles are flung to the outside, and they, due to their inertia and the larger size of them, they hit the side of the cyclone, they start to slow down, and then they slowly spin out and are collected in what we call the grit pot at the bottom of the cyclone. On the other hand, the smaller particles, they remain suspended in the air, and they travel up through and exit the cyclone onto our filter. Now, I thought this was a really good visual representation of what it's actually doing. And I'm sad that it's not actually spinning, but you can see that the yellow particles are the ones that are larger, that are spinning out and dropping down into the grit pot. And you can see these gray ones are the ones that are smaller, that are remaining suspended, that are traveling up. And in this case, they're being removed from the actual industrial process. But if you can imagine on ours, it is traveling up, and all these particles are smaller than 10 microns. And all these particles are being collected on our sampling media that we are sending off to the lab to be analyzed to tell us just how much respirable dust and how much silica is in that dust. So as we go a little bit deeper into the cyclone, there are a number of factors that influence the collection efficiency of a cyclone. Obviously, your particle size distribution. Each particle or each cyclone is not very effective at collecting very, very small particles. And now, like I said here, that it works in our favor because that's what it's designed to do. It's designed to collect those very small ones that are making its way deep in our lungs, as well as filtering out or removing the ones that are not going to impact our body near as much. As you can see with this particular cyclone, it is very long, and this one was designed to work for a very specific process, just like all the cyclones that we use in industrial hygiene. If you look at each one is very unique, has different attributes, they're run at different flow rates, and all that influences and impacts how well that particular cyclone is going to work. Some things to consider is if you're running your cyclone at a too high or too low of a flow rate based on the manufacturer's actual flow rate that it needs, it's going to impact that, and we'll get into a little bit more of that later on. If it's super dry outside, if it's super hot, if it's wet, if there's water being shot into your cyclone, obviously that's going to impact your readings. And so keep in mind that especially with the cyclones that we're talking about, is they require some additional maintenance. The inside of the cyclones can become coated with a fine layer of dust that will continue to build up over time if it is not cleaned out. And what that's doing is it's effectively reducing the size of the internal diameter of that cyclone. And so what you're doing is you're making that curve tighter. And so what you're going to end up doing is spinning out more smaller particles than you would otherwise. So you're effectively reducing your cut point if you choose not to clean your cyclone, which is not a good idea. Other things that can really impact it is blockages. There's been times when I've been sampling underground at the mines, we get our cyclone back, and there is a literal chunk of dirt that is stuck inside of the inlet that has blocked all but, a quarter of the hole. Obviously, that is going to impact how much dust your cyclone is collecting, and chances are that that particular sample is not going to be a good representation of what the actual dust exposure would have been like because it was blocked. So this is a really fun 3D model that I took a couple different views of to show you what the inside of an actual cyclone looks like. This is the SKC aluminum cyclone. You can see over in the far left picture that this is our inlet over here. As we kind of rotate that clockwise, you'll see that there is the vortex generator right here, so that the air comes in through this side hole and it starts to spin around. Those larger particles, as they come in, because of their inertia, they're hitting the side of the cyclone and they're spinning down, and then they're dropping out the bottom where the grip pot would be. In this particular model, I don't have a grip pot, but you can imagine on the very bottom of this, the grip pot is there and it's covering the bottom inlet. So as we look at it from a different angle, we see that depending on how you clean these cyclones, it may impact how much dirt or debris is left inside of the cyclone. If you were to take this cyclone, clean it out with water and put it up on its end, you'll see that there's a lot of spaces for that dust and debris to collect inside down here in the top chamber. So for this particular one, after you clean it, you want to make sure that you stand it up on its end to make sure all of the water and whatever debris is in there is draining out through the bottom of this cyclone, not turning it upside down and having all that dust and debris collect up here toward the top. So I've never seen the inside of a real cyclone for an IH sampling, so I figured this would be a fun way to kind of see what's, pull back the curtain a little bit, show you what's going on inside, because we only see this side of it. We only see the outside, don't really see what's going on the inside. So, like Mr. Thomas Edison said, if there is a better solution, let's find it. And it's called the SKC PPI. So he may or may not have said that, but we're going to give him credit for saying that either way. So here we are. Here is our PPI that we're going to be talking about for the next few minutes. This particular one, the tan one, is our 2 liter a minute PPI. We'll see as we get further down into the presentation, we have a couple different options for flow rates, but the one that we're talking about here is just our 2 liter. So the basic principles of how an impactor works, it's somewhat similar to the cyclone in that it's using inertia to remove the larger particles, but it's doing it in a very different way. This particular picture over here on the right is a multiple stage impactor, but either way, our dust is coming in through the inlet. The larger particles that have a lot of inertia, they are not able to stay suspended in the airstream, and they are directly impacting on what we call an impaction plate. Whereas the smaller particles are able to stay suspended in the air and able to travel around the different plates all the way down to the collection filter on the bottom. And so to kind of review, as air comes into the impactor, it's accelerated, similar to a cyclone, but rather than using a spinning motion to spin out the larger particles with their inertia, it's using these tight corners, kind of like our body is. As we breathe in, there's a lot of tight turns that are removing those larger size particles while allowing the smaller particle to stay suspended in the airstream. And that's due to its smaller inertia and the ability to just stay in the air. So as we can see here, this is an aluminum PPI. This particular one is a reusable one. There is reusable as well as disposable. Typically, we see people doing a lot of research that load their own samples using a reusable PPI, whereas the majority of people doing industrial sampling, they use a disposable PPI because there's no cleaning. They cover the ends, send it to the lab, and that's it. It's a little bit simpler, a little bit easier to do. If you're doing a lot of samples in a research point of view, being able to load your own samples is a little more cost effective. And so going with something that's reusable is beneficial for something along like that. So what's interesting and what's different about this particular impactor versus this one right here, this one uses 4 different sized inlets to capture 4 different sized parts of that respirable curve. And so as air travels in through these curves, you'll notice that the inlets do not line up. Directly under this inlet is an impaction plate, same with this one and all the rest. So those larger particles that can't make that corner to get into the secondary inlet impact directly on this oiled impactor here. Whereas the smaller particles that are in the airstream, they're able to make that corner and travel through that next inlet and then collect on your 37 millimeter filter below. And this is what is, the whole assembly is sent to the lab, but this is the filter that is being analyzed to see how much respirable dust and silica are on that. So the three different disposable PPIs that are made are a 2 liter a minute, a 4 liter a minute, and an 8 liter a minute. Now, earlier we talked about that size-selective sampling is very picky when it comes to flow rate. If you use a flow rate that is too high or too low based on the designed number, you're going to either undersample or oversample for the particles that you need. So typically for a full shift sampling event, a 2 liter a minute PPI is going to be the choice. The one on the left, the tan one, is by far and away the most popular option that we make. But what's really nice about having an option for a 4 liter and an 8 liter a minute is if you're doing sampling with low dust, or you're trying to collect as much dust as you can in a very short period of time, that's when these higher flow rate options really come into their own. So for example, if you're using a detector tube or a charcoal tube, if you're trying to get more of the chemical through that tube, all you do is you increase the flow rate. You can't really do that with a size-selective sampler because of what we've already talked about. And so if you notice, as you look across the different PPIs, you'll notice that the inlet sizes, the holes, are very different. So these have been specifically tuned to a 4 liter a minute as well as an 8 liter a minute flow rate. And where that can really be important is if you are trying to take a short 15, 20-minute sample on somebody doing a task, you may not get the amount of dust you need on the filter for the lab to even analyze it if you use something in the realm of 2 liters a minute. Whereas if you use something that's 4 liters a minute, that's twice as much air coming through that filter, or 8 liters a minute, literally 4 times as much air and dust coming through that filter, you're much more likely to be able to have a viable sample that you can send to a lab to be analyzed and still meet the minimum dust requirements on that filter for them to analyze. So in short, 2 liter a minute PPI for multiple hour sampling, full shift sampling, or the 4 or 8 liter a minute PPI for task-based samples, or for areas where there's not nearly as much dust, where you've had a hard time meeting that limit of detection from the lab. So some additional advantages over a traditional cyclone is there's a nice little calibration adapter that snaps over the top of it. If you've ever had the privilege, or we'll call it privilege, to use a calibration jar, you know that there's a whole bunch of issues that go along with those. So having a sealed adapter that goes over the top of the PPI makes calibration or flow verification much, much simpler. The nice thing about the PPI is it does not matter if the PPI is tipped upside down to the left or the right. We'll get into that a little bit later on with the cyclone. But with the cyclone, if you were to tip that upside down, everything that had collected in the grit pot has a chance to travel back up through the cyclone and be collected on your filter that you send to the lab. Effectively, you are increasing your exposure even though all those particles were already spun out. So that's not an issue with the PPI, which is very, very nice. There's no cleaning, especially we're talking about the disposable ones. And when you're done sampling, you do your post flow rate verification, you cap it, you send it to the lab, and that's it. That's all there is to it. It's smaller, it's easier to use. Workers prefer to use the PPI because of its size. It's not nearly as big or bulky, and you don't have something hanging on your lapel that's constantly swinging around the entire day. The nice thing is Rayco is able to procure these for any of those that are doing their rental program, which is really nice. And it's, in the long scheme of things, having something that is simpler and easy to use from a technician and more accepted by the worker makes our job as an industrial hygienist much easier in the long run as well. So from a regulatory point of view, both OSHA and MSHA recognize the PPI as a viable way to sample. If you look over here on the left side of the OSHA regulation, it says incorporating the ISO SAN convention in the definition of respirable crystalline silica will permit employers to use any sampling device that conforms to the ISO SAN convention. There's a variety of ones they list, as well as personal impactors. You'll notice 2 to 4 liter a minute impactors. There's talking specifically about the PPI here. Over in the MSHA regulation, it says the verbiage is very similar. It uses PPI a bunch more. This last sentence on page 28331, it says under the final rule, the PPI sampler is acceptable. So knowing that you have the blessing of OSHA as well as MSHA to be able to use these in your on your sites makes it much simpler, and also there's a good peace of mind knowing that it's viable to use. So as far as sampling for silica, if you've never done it before, here's a basic list of everything that you're going to need. You need a constant flow pump. What that means is it's a pump that has a flow that is going to maintain the exact same flow throughout the entirety of your sampling. And to check that before and after your shift, or before and after the sampling event, you need a flow verification device. In the past, these were called calibrators. ASTM has asked us to call them flow verification devices now, so there it is. You need your size-selective sampler, whether a PPI or a cyclone. This is really important, and I want to emphasize this, and I'll do it again later on. To do respirable dust sampling as well as silica sampling, you need to have a pre-weighed PVC filter in either your cyclone, your 37mm cassette, or your PPI. Pre-weighed because half of the analysis that's done on that filter is gravimetric, meaning that the pre-weighed PPI has a starting weight of what it was when it got there. You have it now, you sample with it, you send it back to the lab. They're gonna re-weigh it and see what the difference is from the pre-weight to the post-weight, and that is how much dust they will know is on the filter. So if you are using a non-pre-weighed filter, you are not getting nearly the benefit that you will need, because you won't be able to know how much respirable dust is on there. You don't know how much % silica is in the sample. It really gives you very, very little information. So if there's ever a question of should you be using a pre-weighed cassette, if you're wanting to know what respirable dust as well as the % silica, the answer is yes. In almost every instance, using a pre-weighed filter is the way that you want to go. There's very, very few instances where using a non-pre-weighed filter is what you want. And if there's ever a question, you're more than welcome to contact your analytical lab. You're more than welcome to call and talk to me. But in almost everything, again, pre-weighed cassette. Obviously, you want notepads and pens for taking notes, and a camera and a phone if it's allowed. We've all heard that a picture is worth 1,000 words, and a video is worth whatever the conversion is for a picture. But being able to have documentation, pictures of what's happening, it just makes it so much easier for when you get the sample back for interpreting the results, being able to understand what's going on. Like, for example, if you took this picture and the individual that you were sampling is just downwind on the left of this, that tells a very telling story of where all that dust came from. So being able to incorporate pictures into your reports makes a world of difference when it comes to being able to understand and explain the results. So the nice thing about this too is this is expensive equipment, and up until a certain point, buying it can be very prohibitive. The nice thing is if you're trying to start your sampling, you don't know how much you're going to have to do, you're able to rent all this equipment through RACO, which really lightens the financial burden on yourself, as well as knowing that you have the support of a company like RACO that's going to take care of its customers. So if there's ever a question on what equipment you need, what pumps you need, what flow meters you need, RACO is a really good resource to help point you in the right direction of what that might be for your particular need. So this is a screenshot of a YouTube video that I did last year on how to properly check the flow and adjust the flow of a pump when using a PPI. This is just in general what you need. You need a pump. In this case, it's the AirCheck Touch. You have a representative PPI for the actual flow rate verification. You have your calibration adapter. You have a checkmate, which is a way, it's a flow meter. You have a couple different lengths of Tygon tubing to be able to connect your pump to your calibration device or your flow meter device. Still catch myself saying it. But yeah, so if this is a video that anyone needs, I'm happy to forward the link. It walks you through the entire process, which makes it really simple and really easy. So included in that video as well is some proper placement of a PPI or a cyclone. You'll notice that it is clipped within his breathing zone, and your breathing zone is a zone which is about 10 inches around your nose and mouth. So what I also want you to notice is his hose is completely contained within inside of his vest. There's nothing that's hanging down that's gonna catch, that's gonna create an issue for that sampler or for the person being sampled. There's been many times that I've seen people set up sampling events and their Tygon tube is just flopping around. And what it's doing is it's really setting that person up to snag that, which does two things. As soon as it snags and they keep on walking, it's gonna like very quickly eject that cyclone or PPI or whatever it is off their person and fling it upside down into the wall, into the ground, or whatever it might be. So making sure that that Tygon tubing is completely secured inside of either their vest, a shirt, whatever it might be, it's going to be a huge plus for them, and it's going to make sure that you get a viable sample. On the other hand, this particular picture, you'll see that I've seen this before. It blows my mind, but sampling, down at your hip, this is obviously not your breathing zone, as well as the very, very loose Tygon tubing that can catch. In the video, if you watch it, you'll see that as he stepped into his cab, this tube catches right on his shifter up here, and it just creates issues for everybody. So do yourself a favor, do your teammates a favor by always making sure that your Tygon is secured, whether in a vest or in some other way that's not going to allow it to snag on things as people are walking around. So here are some don'ts of sampling that I want to cover. In general, you always want to make sure and do a pre and a post flow verification. This is documented on a paper. You check it before you sample, you check it after you sample to make sure that your flows are within 5% of each other. As you do that, based on how much time you sampled, you know the flow rate, so you can then calculate a volume of air that came through that particular cassette. There's a formula for that. I'll show you that on the next couple of slides. Not taking notes in the field, like I said, doing everything you can to take good, productive notes. If you can take pictures, if you can take videos. I never got back from a sampling event and said, man, I wish I would have taken less pictures, or man, I wish I would have taken as much notes. It's always the other way around. Man, I wish I would have taken just a couple more pictures. I wish I would have, noted a little bit more about this. So while you're there, observing the process, checking in throughout the day, taking as many notes as you can is going to help you tell the story of that sample throughout the day. Like we talked about in a couple of slides previous, not sampling in the breathing zone, we are concerned about what's going inside of your mouth. We are not so much concerned about what is happening down at your waist, or heaven forbid if it comes off your lapel and it's dragging along the ground. That is not the type of sampling that we want to do. And lastly is not using an accredited lab. There are a number of really awesome accredited labs out there in the world that we can use. Do your homework, figure out what lab is going to be accredited that will analyze your sample according to the NIOSH methods or OSHA methods that are going to do a good job. They've been blessed. I can't stress this enough, to be able to use an accredited lab. Don't shortcut yourself to save a couple bucks. So as far as some of the don'ts of cyclones is, if we invert this cyclone, you can imagine that everything that we have collected has that opportunity to travel upside down and travel up with those smaller particles and be caught on your filter. This, again, will artificially elevate your results. You'll end up with larger than respirable particles on that filter. It's going to skew your results, and more likely than not, that particular sample is not going to be valid, and you'll have to take that again. From all of the samples that I've taken, specifically when I was underground, the main reason that caused us to invalidate samples is our cyclone was turned upside down. That looks like somebody crawling under a truck, being very, very helpful and taking off their pump and cassette right before they give it to you and turning everything upside down. You getting to them to take it off, and they've already taken it off and put it upside down on the table. There's too many scenarios that I've encountered that inverting the cyclone it's just kind of a death trap for samples. We talked about it a little bit earlier, but not cleaning your cyclone. as you can tell from this particular picture, dust will collect inside of the cyclone and effectively reduce the size of the diameter, which is going to start spinning off more and more of the larger particles and artificially reduce your cut point. We've already talked about using the incorrect flow rate, and we'll talk about it a little bit more as we go down. Operating without a grit pot. So these cyclones are designed to have air come through the inlet to do their cycloning action to spin out the larger particles. If you had removed this, we'll call this bottom part the grit pot, if you'd remove that, what you've done is now you've created two openings to the cyclone. So air is coming in through the top, it's also coming in through the bottom. That bottom air is disrupting that vortexing, that spinning motion of the particles, and you're going to be collecting particles inside of your filter that are not, they're not following that ISO curve. So if you ever have, or if you ever find yourself sampling without a grit pot, just understand and know that that sample is not going to be valid. This last one is not using multiple cassettes when sampling in high dust tasks. And what I mean by that is, according to the NIOSH 7500 analytical method, you can have a maximum of 2 milligrams of dust on your filter. As you get more than 2 milligrams of dust on your filter, it starts to first, it starts costing you more money from an analytical point of view, but secondary is you're reducing the validity and the accuracy of those samples based on how much additional dust is on those filters. So by splitting your sample throughout the day, maybe every 3-4 hours going when you're checking on the individual that's in a very dusty task, changing that cassette throughout the day will alleviate not only the extra costs of having to split samples, but also give you a more granular look at what happened throughout the day. There were certain times when we were sampling underground that we would change the filter every single hour throughout the day, so we could get a really good idea of what was really adding to his exposure. Was it, task A, B, C, or D? And then based on the sampling that we did, we could start narrowing in on which of those tasks is contributing to the very, very most to his exposure. So try that sometime. So as far as don't for the PPI, the main ones are going to be incorrect flow rate and not using multiple PPIs for high sampling tasks, very, very similar to the cyclone. You're going to run into the same amount of issues, the same types of issues. The nice thing about the PPI is it can handle about 6 to 7 milligrams of dust on the oiled impactors before you start overloading the impactors and dust starts spilling onto the collection media below. So for the same reasons that you want to use multiple cassettes throughout the shift on really dusty tasks, the same thing goes for using multiple PPIs on those particular type of tasks. So briefly, we're going to talk about flow rates and how they impact the cut point. They are inversely related. So the higher the flow rate, you're going to result in a lower cut point. The lower the flow rate, you're going to result in a higher cut point. So as you kind of chew on this, let's look at this particular example to give you an idea of what I'm talking about. So we're looking specifically at the aluminum SKC cyclone that has a flow rate of 2.5 liters a minute. So on this graph, you see this green line right here. This is our convention where our 50% cut point is at 4 microns. So let's look at this the yellow line, which is this particular cyclone operated at 2 liters a minute. So you're half a liter a minute under sampling. So what you're doing is you're shifting your cut point to the right. So it's now where your 50% cut point is between 5 and 6 microns. On the other hand, if you crank that up to 4 liters a minute, you have moved your cut point all the way down to, say, 2.5 liters a minute. What this does is it's going to either over sample or under sample the particles that we want to to have analyzed. And so either way is going to give you a different result than what you want. So being able to check and recheck what flow rate your sampler is designed for before you sample is a whole lot easier than doing a week's, a month's, a year's worth of sampling at the wrong flow rate, and then figuring out how many of those samples are even remotely valid to help tell the story of what happened. Now, last slide to give you kind of a visual example of what this might look like is if you can imagine going around a sharp country road in a nice F1 car. These smaller particles, just like the F1 car, are able to stay suspended in that airstream, whereas these larger particles, much like the semi, as you start increasing that cut point, more and more of these larger particles are dropping off and not being caught on your filter, whereas they're being spun off and not collected at all. So if you look at this particular graph, if you were to operate that at 4 liters a minute, you are collecting, anything over 4 microns, you're almost collecting 0% throughout the entire thing. Whereas operating at 2.5 liters a minute, you're collecting 50% of those particles. So not to beat a dead horse, please double check your flow rate before you sample. It'll make your life so much simpler, just I promise. So after a sample is taken, you are going to check the flow rate after the fact. You are going to have a start time and a stop time of when you turn the pump on and off. And this particular example, if your pump ran for 600 minutes, you operated at 2 liters a minute, you're going to end up with a total volume of 1,200 liters, or 1.2 cubic meters, which we will write down on our lab chain of custody. With this volume, they will put the milligrams or the micrograms that are collected, that they find on the filter, and they can give you a final concentration of what your dust concentration is, both silica as well as respirable dust. So how are samples analyzed? This is a very brief, high level. I'm not a lab chemist, but I hope this helps shed a little bit of light on how this actually works. So samples, they're received by the lab. From there, the first thing they do is they take that cassette out of the site, out of the 37 millimeter cassette or out of the PPI, and then they weigh it. Now, again, I've already said it before, but we'll say it again. You have to use a pre-weighed filter in a cassette to be able to do this type of analysis. This is your gravimetric analysis. That's how much you know how much respirable dust is on that filter. And without the pre-weight, you will never know that. So a little point here is analytical error between the PPI and a typical 37 millimeter is the same because they are both handled the same way. They're both analyzed the same way, which makes it really nice for the lab. After they weigh it, they digest the filter in tetrahydrofluorine, and once that the filter and all that dust are completely dissolved inside of that solution, they pour that into a funnel. They hook that into a vacuum pump and concentrate that on a silver membrane filter. So after that solution is dumped out, this little picture right here is kind of a representation of what that might look like. Once they have that done on a silver membrane filter, they're going to feed that into an XRD machine. And from there, they're shooting X-rays at that concentrated bit of dust and silica. The different X-ray beams are coming off at different angles, at different intensities. And based on which polymorph you're trying to analyze, whether it's quartz, cristobalite, or trinomite, they all have their individual signatures that the machine can detect and tell you just how much silica is in that particular sample. So once they've done this, they put that all on a report, send it back to you. Therefore, you have the weight of your respirable dust. You have the percent silica in each of those samples. You know how much quartz, how much cristobalite, how much trinomite, and it tells you the full story of what happened for that particular sample. So now The next little bit is going to be how much things actually cost. So I'm not going to go through every little bit. High level, it is not cheap. It is something that is an investment, not only in the company that you're working for, but also in the health of the person that you're sampling. You're using these samples to see how much dust is in the air, to know what controls to put in place, to know what you have to do next to make sure that they are protected. One thing I do want to say is, based on what we talked about earlier, in that 2 milligrams of dust that's allowed under the NIOSH method, if you get up to where you have, say, 7 milligrams or more of dust, your analysis goes from, say, $95 up to $190 because they're analyzing it in a different way. So again, we're trying to keep all of our samples at 2 milligrams or below on a filter to make sure you have the most accurate samples, as well as being the most cost-effective for what you're trying to do. So some additional costs to consider. I'm not going to go through every single one of these. Resampling due to invalid samples. This is what I was talking about, flipping your cyclone upside down, dragging in the dirt, a number of things that can cause invalid samples. Follow-up samples, this is a big one based on what your results are. If you're trying to follow the MSHA rules, they're very precise in how many samples you have to take based on what your results are, and it can vary between once a year and as many times as you need to figure out what the problem is. So obviously, implementing controls is a big part of what we're trying to do with silica sampling, and it's a cost all of its own. So we have some regulatory issues and some labor costs. What I thought was really interesting in the MSHA final rule is they give a really good breakdown of how much they calculated sampling to cost, not from an analytical point of view, but just from a labor point of view. So if we look at a mine site that has between 21 and 500 people, they calculated that each sample you take costs $380. Now that is your time, that is part of your salary, that's the travel to and from work, that's all the things that go into taking that particular sample. So when you start thinking about samples that are invalidated from, say, a cyclone tipping upside down, your pump dying halfway through the shift, whatever it might be, those costs seem to add up relatively quick. So obviously, this does not cover any of the cost of lost production that caused the supervisor or the person that you were actually sampling, but it's real costs, and it's something to consider as you go out and try to get the most out of your samples and get the most productive samples that you can. So to kind of finish things up, I chuckled whenever I see this picture, because sometimes after a full shift of sampling, this is exactly how you feel. You're beat up, you're covered in dirt. Depends on how many times you trip underground, but you could be covered in blood as well. A few reasons to use the PPI is it's a lot faster to set up, to deploy, to take down. It's very simple to use. There's fewer voids or resamples because you don't have nearly the same issues as you had with a cyclone from tipping or some of the other issues that go along with it. I've never talked to a worker that's used a PPI and a cyclone that they say, hey, can I please use a cyclone again? I'd much prefer that. It's quite the other way around. It's people are using a PPI, they much prefer it because it's smaller, it's less obtrusive, it's not swinging around them all day. It's a very small, compact, and nice thing for them to wear. Obviously, wearing any sampling equipment is not ideal, but it's trying to help them have the best experience and get you the most accurate data that you can. There's no cleaning repairs or spare parts. And ultimately, when you're purchasing a PPI to use, you're paying for convenience. It is simpler for you to use. It's better accepted by the worker. And overall, it just makes your life easier and simpler as an industrial hygienist. And ultimately, that's what we're all trying to do, is do our job, do it in the most effective way possible, and obviously have a little bit of fun doing it. So With that, that is what I have for you today. So if there are any questions, please let me know.
Great work there, Dusty. We do have quite a few really high quality questions here. The biggest one here, first off, is it appropriate to use a PPI with an 8 liter per minute flow rate if the operation that we are trying to characterize is very short in duration, around 10 to 20 minutes? It would give us the required minimum volume per the NIOSH method, but since humans don't typically breathe at 8 liters per minute, is it truly representative of the exposure?
I think that's a great question, like you said. And answer to your question, yes, 100% is a good, viable way to capture that much dust. What we're trying to do is you're trying to capture as much dust as you possibly can to get on that filter for the lab to actually be able to analyze it. Now, understanding that most humans don't breathe that much, what we're trying to do is get a representation of the actual concentration in the air. And that's what those higher flow rates allow you to do, is collect a vast much more air than what we could otherwise without changing that particular respirable curve. So that's where those 4 and 8 liter a minute PPIs really do a good job, is collecting a lot of air and dust in a very, very short period of time.
Thank you, Dusty. Next one is, how difficult is it to reload the PPI and be sure that you have not affected the pre-weight of the filter?
That's a good question. I am not someone that routinely does this, but I know from a lab point of view, there's a very specific process that they follow. They have procedures that they follow to make sure that that particular set of circumstances is followed so they can get the most accurate results. I think it's probably like anything we do, the more you do it, the more familiar you are with it, the better results you're going to get. And so that's why, particularly for me, I let the labs do that, because they do it much, much better than I probably could.
Makes sense. And then the next one is, will elevation, moisture content, relative humidity, or mass of the dust affect the accuracy of the test?
So everything is going to impact the way that the sampler works, whether it's your humidity, elevation, whatever that might be. What you're trying to do as an industrial hygienist is reduce as many of those variables as you possibly can. That's where doing your pre and post flow verification to make sure that they're flowing at the same time. The humidity is obviously going to add weight to that filter. And so when that filter is received at the lab, they let that sit for a certain amount of time to equilibrate to the same humidity it was when it was first weighed. There's a lot of things that go into making sure that when the lab gets that sample, it's going to be the most accurate that it can possibly be, whether that's from a cyclone or from a PPI. And so what you're trying to do throughout your day of sampling is do everything you can to reduce any additional sampling error into that equation, to make sure that the results that you get at the end are going to be valid. And so in answer to your question, yeah, that's for sure.
I think that's probably where the chain of custody form has a big impact too, to ensure that the lab is aware of exactly what is going on in your testing scenarios, so that they can account for that.
Yep.
And then we also have, in a low dust environment, would a 4 liter per minute PPI still work for a full shift sample? What's the best way to determine the appropriate flow rate to sample for silica?
That's a great question, and yes, absolutely. When we look at the NIOSH method, the 7500 method, you're looking at the amount of dust that is needed to run a sample. So you have your low and your high. So what you're trying to do from figuring out what flow rate you use, at first it's going to be a little bit of trial and error. If you have a lot of dust in the air, obviously you don't want to use a higher flow rate PPI because you're going to overload your filter and it's going to cost you more in the end. So what I would say is maybe take a 4 liter a minute PPI, use that for half of a shift, and then use the other 4 liter, then use another one for the next half of the shift. Based on what those results tell you, you'll know, am I under, am I over? It's going to give you an insight into where your next samples should lie when it comes to flow rate. So taking some liberty to look in the area that you're working with, if there's not a lot of airborne dust, then maybe going for it and doing a 4 liter a minute for the entire shift might not be a bad idea. But if there is a question, being able to split them up throughout the day is going to help you really determine where you should end up in the end as far as what flow rate makes the most sense for your process.
Perfect. I also just want to say that I know that we have reached the hour mark here. If you need to leave, that is just fine. We understand that. However, we will continue answering questions because we are now able to go over that allotted time. These will all be, the recording will all be posted onto our webinar tab underneath the training center with this recording of the answers here. So we're going to continue answering some more of these questions. Stay for as long as you can. Next one that we have here is how would one tell if too much dust is getting into the sample? We actually have a few people that have asked this. So
that's a really good question. And there's a couple different things you can do. In short, the answer is you don't know. But the long answer is, depending on how you're taking the sample, there are ways to know how much dust is going through that. And what I mean by that is there are real-time dust monitors like the AES SM7204 that on their latest software release, based on how much dust comes past their light scattering sensor, they can tell you how much dust is being collected on that filter. So if you're using an instrument like that, you can monitor that throughout the day to see how much dust is on that filter. And when you're getting close to that 2 milligram limit, you can remove that cassette, put in a new one, and do the same thing again for the remainder of the shift. Outside of using a device like that, it's just kind of one of those things of trial and error and trying to use your best judgment based on what tasks are going on, how much dust is in the air. And like I said, if this is your first time and you don't know, splitting up the day into multiple samples will help you understand just how much dust is on each of those particular filters and allows you to make a better choice for all of your follow-up samples after that.
great. Next one is the PPI suitable for other respirable size particulates? Any it should not be used for?
It is designed as a respirable sampler. And so, for example, for silica sampling, you're using a PVC filter inside of that particular PPI. There are other metals specifically that have their own respirable exposure limits that need to be analyzed on, say, an MCE filter. And so there are a lot of companies that are using a PPI with an MCE filter to measure their respirable manganese, as well as having, running just a standard 37 millimeter cassette on a different pump to figure out what their total manganese might be. And so, in short, it's designed as a respirable size sampler. So anything that's going to be respirable in the air would be appropriate to be collected on a PPI. You would just need to determine what filter media is going to be the best choice to do that. And that's where having an accredited analytical lab is going to be very, very helpful to you. Is picking up the phone, talking to them, and have them walk you through which way you need to go for that particular sampling event that you're trying to do.
Yeah, that's great. We work directly with several labs all across the country. ALS, Bureau Veritas, SAI, a bunch of different labs that are accredited, that we can refer you to the different labs to be able to get you the answers correctly, to ensure that you're taking your samples correctly and getting the kind of data that you need to keep your workers safe. Another one here. Have you ever ruined a sample when removing a cyclone from a filter housing? Dave has lost a sample that way in the past.
I personally have not, but it would not surprise me if that happens out there. There's, depending on what cyclone you're using, if there is bands around the cassette or not, I can see how that could be problematic depending on what sampling device you're using.
Perfect. And then this will be our last question that I'm seeing here, potentially one more if another one pops in the meantime. But MSHA is sampling at a 2 liter per minute rate using a cyclone and then converting the results for the mine operators to an 8-hour TWA. How is that conversion done? Does it still meet the NIOSH methods?
So that is a really good question, and I've done a whole number of webinars on that particular thing. What you are doing is effectively you are taking your result that originally was averaged over a 12-hour shift, and you're just compacting it into a 8-hour shift. And so I'm happy to, whoever this person might be, I'm happy to walk them through the formula. It's in the actual MSHA final silica roll. It's not a hard equation. You're basically taking your flow rate and you're multiplying that by 480 instead of your true runtime. Like I said, all that's doing is just taking your results that happened over a 10, 11, 12-hour shift, and it's compacting it into what would be an 8-hour shift. So, for example, if you had a result that was for your 12-hour shift that would say 50 micrograms per cubic meter, once you compress that into an 8-hour time-weighted average, it's more along the lines of 58 or 60 micrograms per cubic meter. It's always going to increase when you're compressing from a larger time frame into a smaller time frame.
Makes sense. All right, last one here. When using multiple cassettes, do we need to pre-calibrate and post-verify each time that we change the cassettes? You
do not. You have a representative either cassette or PPI when you're doing your pre and your post flow verification, presumably from the same lot that your samples are being taken from. And so every time you change a cassette or you change a PPI, you are assuming that it has the same back pressure as the other ones in that lot.
Sounds great. For the other additional questions, from what I'm reading here, I will connect you directly with Dusty and get him over the questions and your information so that he can work with you further on getting those answers to you. I think that it would be best for him to be able to work directly with you on these additional questions. In closing here, Dusty, thank you so much for enlightening us with your presentation today. Any specific questions in regards to equipment, I highly recommend viewing our training center on our website. The training center has videos connecting to just about every single one of the pieces of equipment that we have in our rental fleet. All of the webinars are posted on there, and everything that is on that training center is free for anyone in the industry to view. We want everyone to feel like experts on every piece of equipment and different kinds of sampling methods and procedures, so that we can have the collaboration to keep our people safe. We have those training videos demonstrating equipment operation, including all the past webinars and blog posts for educational content on the different industry standards. Also, feel free to give us a call at 866-RENT-EHS or 866-736-8347. You can also reach us by email at rentsconfirmation@raycorents.com. Rayco Rents will be at many future conferences this fall, including but not limited to the Rocky Mountain Mining Conferences and several all across the country local chapter AIHA conferences. Come visit our booths. We would love to speak with you further about new products in our rental fleet and how we can continue providing great rental services to you and your companies to help keep people safe. We are always open to new topics for future webinars. If you have a subject you'd like to see covered, we would love to hear your feedback. Please fill out the post-webinar survey or send us an email directly. Thank you everyone for attending our webinar and have a great rest of your day. Thanks again, Dusty.
Thank you.